2018 LA. That's right.
All right. So later today, we're going to start with our planetary defense exercise. But last year, we had a real impact. A small object, 2018 LA, about 2 meters in size, reached the Earth on June 2nd, 2018. And here, I think, if the video works, you can see a video that was taken of this object as it was getting to the ground. And that's my favorite one. I found that on the website of the American Meteor Society. So that's real time when it happened. Okay, we know that small objects do reach the Earth on a frequent basis. We know that from population models, and we know that from direct experience, because before this object, we had other two asteroids reaching the Earth, 2008 TC3 and 2014 AA. They were both about 5 meters in size, discovered by the Catalina Sky Survey, only 20 hours before impact. So we do not have that much time to deal with these cases. And so those are good tests for us to see how we are prepared and how we can provide impact predictions on a timely manner. So for this reason, at JPL, we built the Scout system, which tries to provide hazard assessment as soon as an object is discovered. And this means mining the confirmation page of the Minor Planet Center, where all the possible objects that still need confirmation are posted, waiting for more data. But we don't wait. We try and see immediately if some of those could be on an impact trajectory. Now, if you build a system like this, you wait every day until you get a message like this, and then you get really excited. So on June 2nd, we get this message saying that this strange object, ZLA F9b2, had a 5% impact probability. 5% is large enough that we should take it seriously and see if we can better understand what is going on, if we can get more data and assess how good the astrometry that we got so far is, and so on. Along with that message, we also got this impact corridor map, where you can see we start from an impact at 1330, which is only a couple hours after discovery on the east side, and then we move westward until an impact at 1715. And that is for a 5% impact probability, which means that 95% of the possible orbits actually miss the Earth, and they are located on this side. Let me see if I can, it's pretty faint. Anyway, here you have a grazing impact, essentially. And then if you are west of that, you're just missing the Earth. But we also know that the object is not that big, because all the solutions that correspond to an impact have an absolute magnitude between 30.5 and 32.2. That means 1 or 2 meters. So it's not, we know it's not a serious hazard, but it's something that could happen. Now, this assessment was based only on 11 observations from the Catalina Sky Survey over an hour and a half. That's a short arc. That's not a lot of data to work with. And yet we found a 5% impact probability. And of course, when you get a message like that, you're ready to act and to do your best. Well, not quite like that. That was a Saturday, and a bunch of people working on NEOs were attending an NEO workshop in Munich. And since that was a Saturday, that was our day off, and we went to visit the Riss crater in Germany. We were having a nice lunch with very crappy cell phone reception, and we got that message, and oh my God, what are we gonna do? So we try and contact other observers and ask them, can you please see if you can get more data? We asked the Catalina team, can you please check that the astrometry is good and see if you have additional detections and so on. Marco and Gerard even drove away from that spot to find a better cell phone signal and be able to reach someone. And then we get to work. And so we go and we try to spot these objects. And from this picture, you can really see who cares about planetary defense and who doesn't. And Gonzalo, I'm gonna put you on the spot. You keep looking at the camera as if nothing was gonna happen. No, but jokes aside, the Catalina team did a good job. They were actually able to get an additional detection that was missed in the first submission to the MPC. So we get a little more data. They remeasure some of the observations that were a little noisier than they should have been. And they also communicate some information about the uncertainties. And so we can use all that information to improve our assessment. And now the impact probability goes up to 30%. So that's pretty high. It doesn't happen all the time. And the impact corridor, as you see, has not changed. The only difference is that the fraction of orbits that actually misses the Earth is much smaller. It's only 70% now. So we have 30% impact probability. And that's all the optical data we had before the object actually reached the Earth. And so we didn't know anything besides that. So how did we confirm the impact? First clue, it was discovered by Kowalski. And this is the same guy who discovered TC3 and 14AA. So if it is discovered by Kowalski, it might be real. If it's not, then we can just leave them alone. Yeah, it's pretty impressive. 3 out of 3, it's hardly just random. But no, there were fireball sightings reported to the American Meteor Society. They were located somewhere along that corridor that I showed. There is another video here. And if you go on their website, too fast. If you go, let's see, let me try again. Okay, there it is. There's another one. If you go on the American Meteor Society website, you're going to find a few more of these videos that show the re-entry of these objects. The other thing, I sent a message to Peter Brown and I said, look, this is my impact corridor. Can you take a look at the infrasound data and see if you can find something that is consistent with the impact? And there is this network of stations that measure infrasound signal, and sure enough, if this comes up, there you go. Here's the detection from a station in South Africa that is compatible with an impact in Botswana, which is consistent with the impact corridor and consistent with the fireball sightings. Then it turns out that Atlas had looked in the right spot to get more data of this object. Unfortunately, they had bad weather, and so they could not get the 4 detections that they usually require in order to trigger the automatic pipeline. They only had 2 detections, and those had to be extracted manually. But eventually, they did extract those positions. They submitted them, and using this information, we were able to much better constrain the orbit of this object. Now the impact probability was 100%. Even though if that was after the impact, it was a nice confirmation that we could have used this data if they were available real time, and we could have gotten a very constrained estimate of what the impact location that is compatible with the infrasound data and the fireball sightings. And finally, there you go. There was a fireball report from the US government sensors, and you can see that's the red dot, and the red dot is within the impact footprint. And so that is compatible with what you would get from optical data only. That refined the energy, the estimate of the energy of the impact, about 1 kiloton. The impact time was 1644 UTC. That's only 8 hours and a half after discovery. This is a really compressed timeline. And the impact velocity was 17 kilometers per second. So everything seems to hang together pretty nicely. And by using that fireball data, we were actually able to better constrain the orbit. Let me go back for a second. So I had all those points that were compatible with the data. The fireball report tells me that it has to be around that part of the uncertainty region. I put that in, and I computed a ground track for the possible, the projection of the asteroid on the ground as it was reaching the ground. And Peter Janiskins used that ground track to go and try and find meteorites. And with his search team, it was successful. It's probably hard to see here. This is the meteorite that he was able to find. So that's another confirmation that the trajectory was good. The impact prediction was accurate. And so conclusions, I think it's fair to say that the system worked pretty well. We have to keep a few things in mind here. First of all, meteor-sized objects are not our main concerns. So that's not really what the system is designed to deal with. And yet, we only had 8.5 hours. We had to deal with this object on a Saturday. So I was not, for instance, close to my laptop or close to my office. My backup, Shantanu, was in California, and he was sleeping when this was happening because it was 4 a.m. So we had to rely on a reliable automatic process. And I think things worked as expected. So that was pretty good. And I think this is mostly useful to put into the perspective of bigger objects that are discovered under final approach. Let's think about a Tunguska-sized object and for which it might be discovered maybe days, more days, or 1 week, 10 days before impact. In that case, being able to predict the impact and the impact location within 1 or maybe 2 days will be very valuable because it would leave 8 days for preparing for mitigation. And so I think this was a pretty successful test. And with that, I'll take questions.
Okay, thank you. I would comment that something the size of Chelyabinsk should be visible with our surveys about a week out. The meter or 2 or 3 meter sized objects only a day. So actually Richard has done very well hitting them 16 hours out. And I hope somebody has managed to scour up a piece of that meteorite to give him so that he can have another mantelpiece. Okay, questions?
David, these objects, they should be pretty frequent. How often should we see this now in the future so that you can predict them?
So I think the frequency for these size range is every couple of years, but half of them come from the sun and half of them come from the nighttime sky. So every 3 or 4 years, 5 years seems like a good estimate of the time interval.
I would concur with that, having done the calculations a few times.
All right, so how far out are you looking for impacts with the original tracklets that you get? Are you looking 6 weeks or for everything? Do you just
30 days.
30 days? Okay.
Okay, is that it for questions?